Okay, so hey everyone, my name is Sam Rothstein, and today I'm going to be giving a presentation about the theory and applications of compressed sensing. Now, I just want to preface by saying that this presentation is extraordinarily unique because it's the only presentation on this topic that is under 45 minutes long. So you're in for a real treat. All right, so we're going to start with an introduction to compressed sensing theory. Now, compressed sensing is also known as compressive sensing or compressed sampling or sparse sampling, is essentially a signal processing technique for efficiently acquiring and reconstructing a signal. And the means by which this happens is we find solutions to a highly underdetermined linear system. Now, there are a few things that I mentioned that I just want to go over briefly. In signal processing, a signal is a function that conveys information about a phenomenon. And a signal can be many things. It can be audio, it can be video, like you're seeing now, it could be speech, image. The list just goes on and on. The next thing that I just want to mention briefly is that in mathematics, a system of linear equations is considered underdetermined when there are fewer equations than unknowns. These are the ones that we hate to solve. I'm sure you're familiar with them. All right, so a presentation on compressed sensing wouldn't be complete without briefly mentioning the Nyquist-Shannon signal sampling theorem. I'm going to try not to say that 3 times quickly. All right, so compressed sensing is essentially based upon the principle that through optimization and some careful decisions, the sparsity of a signal can actually be exploited to recover it in far fewer samples than we would expect. I just want to mention that the Nyquist-Shannon signal sampling theorem is a really important theorem in the field of digital signal processing. And what it does is it kind of bridges, it serves as a bridge between continuous time signals and discrete time signals. All right, so there are essentially 2 conditions under which recovery is possible. The first condition is sparsity, and this requires that the signal must be sparse in some domain in order for it to be recovered. And I think we mentioned this term a few times, and we're going to go ahead and define it a little bit better in the next slide. The second property is incoherence, and incoherence is applied through the isometric property. And in linear algebra, the restricted isometry property essentially characterizes matrices, which are nearly orthonormal when they're operating on sparse vectors. And it's important to note that this is sufficient for sparse signals. Okay, so now we're talking about the first of those 2 conditions, and that is sparsity. So in numerical analysis, a sparse matrix or a sparse array is a matrix, or of course an array, that has mostly 0 elements. Now, as mathematicians, mostly is not sort of a strange word. And so to be specific, there's no strict definition of how many elements need to be 0 for a matrix to be considered sparse. But one common criteria that people use is that the number of non-zero elements is roughly the number of rows or columns. Yeah. So if we have an image of a sparse matrix on the left, and on the right, we have an image of a guy surfing, which looks rather fun, which is actually sparse in some domain. So next we're going to talk about the second of these 2 conditions, and this is incoherence. So in signal processing, coherence is a statistic that can be used to examine the relationship between 2 signals or potentially 2 data sets. But in this case, we're most interested in signals. And what coherence does is it's a measure of the largest correlation between any of the 2 elements in each signal. And essentially what this means is that if the signals have correlated elements, the coherence would be rather large. Now, in compressed sensing, we're mostly concerned with low coherence pairs of signals. Okay, so part 1, we're going to be talking about the underdetermined linear system that we referred to before. Okay, so in this system, we have y as a measurement of the original signal. Phi is the sampling matrix that is used to produce y from the original signal. We also have that phi is incoherent with psi. Now, we talked about what incoherence means in the previous slide. Other thing I want to mention is that x in this case is the signal that we wish to recover from our sample of the original signal, which is once again y. As we can see here, we have a highly underdetermined system of linear equations, which means that we have more unknowns than equations. In order to solve one of these systems, we might kind of think back to some of the classes we took at Swarthmore, but one thing that we can do, a really helpful tool, is you simply just impose extra conditions. Sometimes this works. Okay, so in compressed sensing, we add the condition or more of the constraint of sparsity, right? So we're only going to allow solutions which have a small number of, non-zero coefficients. All right, so obviously not all underdetermined systems have a sparse solution, but we're sort of making the promise that if there's a unique sparse solution to the underdetermined system, then using compressed sensing will allow us to recover that solution. All right, so part two, we're going to talk about the reconstruction method. So as we sort of alluded to before, we know that many signals are sparse, which means that they contain many coefficients that are close to or equal to zero when represented in a particular domain. So compressed sensing usually starts by taking a weighted linear combination of samples in a basis that is different than the basis in which the signal is known to be sparse. Now, the results found by Candace, Romberg, Tao, and Donahue, hopefully I pronounced that right, but essentially the results show that the number of these measurements that we need can be incredibly small, but it will also still contain nearly all of the useful information that we will need down the road. Thus, we have the task of converting the image back to the intended domain, and this involves solving an underdetermined matrix equation, since the number of compressed measurements taken is much, much smaller than the number of pixels of the full image. Okay, so now we have to go back to our initial constraint that the initial signal is sparse, and this enables us to solve this underdetermined system of linear equations. So to enforce the sparsity constraint, when we're solving this system, we essentially minimize the number of non-zero components of the solution. And the function that counts the number of non-zero components of a vector is called the L0 norm. In, I guess, subsequent papers, people have proved that for many problems, it's likely that the L1 norm is actually equivalent to the L0 norm. And what this means is this equivalence allows us to solve the L1 problem, which turns out to be much easier than solving the L0 problem. Essentially, finding the candidate solution with the smallest L1 norm can actually be expressed pretty easily as a linear program. And as you may know, there already exist fairly efficient solutions to solve a linear program. All right, so now that we have tried to go over as quickly as possible, possibly setting a record for covering this topic, we're going to talk about some applications of compressed sensing. So compressed sensing is used in photography. In particular, it's used pretty commonly in mobile phone camera sensors. And at a high level, what this approach does is it allows a reduction in image acquisition energy. And it kind of reduces it by a significant amount. The next thing that I want to talk about is that compressed sensing is actually used to improve image reconstruction in holography. And holography, if you don't know, is a science and practice of making holograms. So in the PowerPoint, I have a hologram of Tupac. So Tupac's not alive, but his hologram lives on. Anyway, compressed sensing is also used in that field. All right, so I'm really running low on time, but I just want to mention that I did actually program up a static compressed sensing demo. There isn't much time for me to go through the code with you, but I kind of encourage you to go follow this link and check out my GitHub and download it for yourself. And you can run your own images through it. You can see how they're sampled and exactly how they are reconstructed based on those small samples of the original image. One thing that I want to mention is that this static compressed sensing uses the orthogonal matching pursuit algorithm, which essentially is a method for finding the smallest candidate L1 norm that we talked about above. And that's all I have. So thanks everyone for watching. And if you have any questions or comments, I guess just post them in the Slack channel.